So technically our next topic isn't really thermodynamics proper. It's what's called statistical mechanics, which is an attempt to relate mechanics to thermodynamics. But really doesn't really matter. What we want to do is figure out what temperature is. And you guys actually probably know that temperature has something to do with the average motion of molecules in a solid, liquid, or gas, or Bose condensate. And basically what I want you guys to do is see this nice 2D demo. There are some ball bearings in there, and it's attached to a mechanical vibrator that I have a signal generator hooked up to. And see if you can see all of the gas laws. So the one that you can't see is Avogadro's law, because there's a fixed number of ball bearings inside of this. But see if you can see the relationships in between pressure and volume as I kind of put this through its paces. And what I'll do is I'll fix volume for one of them. So let's turn up the volume a bit. And voila, that's kinetic theory. So yeah, again, you can see the effect of pressure. I can tell you that it pushed back on my finger a bit when I pressed down on it. And certainly you can see the volume. And the thing that, again, takes the role of temperature is basically how agitated the ball bearings are. So this is going to be our foray into, again, kinetic theory. And we're just going to talk about, honestly, what pressure is, calculate pressure, and then use that to deduce what temperature is. And the way we'll do this is we'll make a kind of toy theory model for a box of gas. And then what we'll do with that is deduce what we can just on purely theoretical grounds about how much pressure we can exert on the side of a box by just smacking stuff into it. The goal of theoretical physics in some sense is to do as much as possible while putting in as little effort as possible. So the way that let's use a completely box, so just L on every side. And let's make the particles inside of the box the easiest particles that I can possibly imagine. So first off, these are perfectly reflecting walls. And the gas is basically point masses. Which means that they don't store any energy inside of them, like they don't have any internal springs or detail. And so what we call classical or Newtonian mechanics. Quantum mechanical particles in a box are a totally different animal. So we'll just let them whiz around and describe their impacting on the sides of the box. And what you'll see is actually in a totally different context. Essentially, you've solved this problem. So there I might have a collision, and there I might have a collision. And you guys kind of know what happens when particles collide with perfectly reflecting walls. So you did this on Mini Project 1, and you know about the Apollo corner cube reflector. And that is the relevant geometry. So what I want to do is I want to figure out pressure. And we kind of already have area, that would be L squared, but I'll leave that for a second. So first thing I want to do is talk about force itself. So you guys are used to seeing force as ma. There's a nicer way of expressing it in this particular case as delta P over delta T. It's nicer because thinking about momentum and reflection is really easy. It's not nicer in the sense that we already have a P floating around, and that's pressure, which is force per area. So I'm going to do my best to make this lowercase and serif and squiggly to indicate that this really is momentum. So this is change in momentum over change in time, which is actually how Newton phrased his second law originally. So this is momentum, and that's pressure. Okay, so now this is 1 over A, delta, delta, change in squiggly P for momentum over some amount of time. Okay, so let's consider just one and only one of these collisions. So this thing comes in, and it bounces off the wall. What happens to the particle after it hits the wall? In a perfectly reflecting wall, well, it comes out, and basically the only thing that changes, let's call this the x direction, is that its momentum in the x direction is flipped. Right? And so easy enough, I'm just considering something bouncing off of this wall that, is a normal pointed in the x direction. Then the change in momentum, px goes to p minus x, then the total change in momentum would be 2px. Right? So thing minus negative thing is 2 thing. So every time we bounce off a wall, if it's this wall with the x normal, we get 2px. If it's the top wall with the y normal, we get 2py. And eventually we'll just say there's no preferred direction, so there's nothing special about the x direction. I mean, so far this is looking really good. We just want to calculate pressure. We know the area is L squared if we need it. We know that delta P, every time we collide with a wall, is 2px. All we got to figure out is basically how frequently we collide with the walls. So how frequently a particle collides with the walls is delta T. And that is the last little bit. So what is delta T? So in a kind of statistical average sense, what this is average time between collisions. And that, I think, bears digging into a little bit because we're doing something that you guys didn't do in mechanics, which is talk about stuff in a statistical kind of way. So basically, the idea is if you think about the wall of this, or you thought about the top of that demo I just showed you, is that there's a whole bunch of things bouncing into it, and it's happening very frequently. And so in a sense, what this feels is kind of an average effect of a whole bunch of them. So let me imagine now that this particle bounces off of this wall, and px went to minus px. So its x momentum got flipped, and then it bounces off of this wall, and then minus px goes to px. And then, sure, eventually it'll bounce off the top. That'll flip the y or the z, nothing to do with the x. But it'll come back and hit x, this side of the wall, that side of the wall, this wall, that wall, this wall, that wall. And so what I can do is I can express actually the delta time in terms of the velocity and therefore the momentum. So what I'm doing also is I'm flipping vx and the velocity. I'm not changing the mass part of the momentum. And so I have delta t, if I think about it. Delta t over distance is vx. I'm not changing its magnitude. I'm just changing its direction. So what's the distance that this thing travels back and forth? Well, that's just L. And what's the distance in between? So actually, 2 ways of thinking about it. One way is what's the total distance in between collisions with this particular wall? It goes down and back, so that's 2. So I have 2L. Or I could think about it as like half the time is to get down, half the time is to get back. But one way or another, I know that I get something that looks like this. And we'll express everything in terms of p. So this is px over m. That's just the velocity. And therefore, I have the final piece. This is the time in between collisions. The time in between collisions is the amount of distance it travels, 2L, divided by the speed, which is px over m, which is just a fancy way of saying velocity. So honestly, we have everything. We have t, we have p, delta p, we have a, and we're ready to just write down what the pressure is in our toy model of particles in a box. So technically this is px, the pressure on this x wall. So what I have is force on the x wall divided by the area, so that's force divided by L squared. So this is mvx quantity squared. Well, let's do it in 2 stages. So we found F, that's delta P over delta T. So writing it in one gross chunk first before simplifying. This is 2 mvx. So that's twice the change in momentum. And then divided by delta T is 2L over px over m, but we can just call this Vx now because we're expressing that in terms of velocity. And then we have the pressure on that particular wall. After some simplification, we get an L cubed, 2's go away, we get a V squared. So we get m Vx quantity squared over L cubed. Or, and this is going to be bad again. So for a moment, you're like, yeah, I got rid of that P, which was annoying me because I have another P. Well, we're going to introduce a V because L cubed is V, but it's the thermodynamic V. So we have V is for velocity, x quantity squared over V is for volume downstairs. And the reason to do that is these are thermodynamic variables, which is what we're looking for. Okay. So last step is that this is on the x wall. There's nothing special about the x wall. This is on the y wall. This is also on the z wall. So what we could do is we could ask about basically an average. And we could average over these 3 directions. And we could note that the average speed of a particle is expressed in the following way. Technically, it's speed squared. So we'll define the square of each of these velocity components, and noting that there's nothing special about each of these directions, so that Vx squared equals Vy squared equals Vz, right? These are, sorry, averages. So the average speed in any direction in this box, basically like one side's not getting hit harder than another side, is all this is saying. Is we can now get rid of the subscript x, and we can say the average p is mv squared over v is for volume, and then let's make it look a little bit more thermal. We get a third over there. PV, hey, this is starting to look good because we have an ideal gas law that has a PV in it. And then finally, this is per particle, right? So we just thought about one average particle. Because this mass is for one particle, that's the momentum that one particle bouncing into all of these walls really rapidly would exert. So for all particles, just multiply by the total particle number. So Nm, there are n particles mass m, and each one of them is exerting this much pressure. So that's a throwback to mechanics. This is kind of how statistical mechanics in some sense works, is you take, a theory, it might be quantum mechanics, it might be classical mechanics, and then you try to map it onto thermodynamic variables. In this case, P is for pressure and V. And then we also have N. We could turn that into mole number if we wanted. But first we want to make a realization about this. because it says more than we thought. So the thing that you can do just without examining this further is realize that you have two thermodynamically accessible things, right? You have the pressure and the volume, and you can make those thermodynamic measurements. And you can use them to determine some interesting microscopic stuff, like the speed of the particles in the box. So basically what I'm saying is if I had a tank of gas and I was doing kind of thermo experiments on it, I was measuring stuff like the pressure and the temperature and looking at this piston, I might be able to actually deduce, because what the pressure tells me is how fast these things are bashing against the top of the cylinder, is I might actually be able to deduce what's called the RMS, root mean squared speed of the particles inside of this cylinder. So that's neat. So the first thing is we can use P and V to reach inside and say things about like, well, how fast is an air molecule moving? The second thing we can do is that this is the left-hand side of the ideal gas law. And we also know that PV equals, so we've got N particles, so I'll use the NKT version. Well, PV equals NKT, PV equals NM squared over 3. So what that tells me is NM mean squared over 3 is NKT. And I'm going to express this in a way that maybe you've already noticed. So let's get rid of the n's. Forget about the other adornment, the average. What really important mechanics quantity has to do with mv squared? Yeah, exactly. So this is basically the kinetic energy, and I can turn it really into the kinetic energy by making it 1/2. It's a funny V because it's an average. It's like kind of the average over all of the possible particular thing. But this is the typical kinetic energy per particle. And what we can do is we can relate it mathematically to the temperature. So that's 3/2 kT. So this is the second and more interesting thing we can do is, essentially what this did is this just proved that the temperature is related to the average kinetic energy per particle. So this is average kinetic energy per particle. And I'll use the same overbar for average. Is 3/2 kT. Okay, so the fine print on that is that we made some pretty strong restrictions. So these were like structureless point particles that bounced off of ideal walls. We'll keep the ideal walls, but we might actually be interested in things that aren't ideal point particles. And this has a name. This is for the monatomic ideal gas, which is to say basically infinitely small, perfect billiard balls like the ones I showed you in the demo. Okay. So let's use this to do some interesting things. Figure out what the average kinetic energy and then therefore the speed of a molecule at room temperature STP is. Let's just pick one. Yeah, let's do room temp. Okay. Again, the fine print is that so far, you probably have seen the 5/2, 7/2, etc. So far, this 3/2, that's only relevant for a monatomic ideal gas. So let me draw a monatomic ideal gas particle. It's just those. So it's really not air. Air is maybe rigid, maybe stretchy diatomic ideal gas. Okay, so what this means is that temperature is about 20 degrees Celsius, that's about room temperature, and pressure is about 1 atmosphere, which is about 101.3 kilopascals. And we've got this version, so we don't have R, we have K. So let's just plug this in. So 3 halves kT. Turns out we don't even need pressure, because this is the average kinetic energy per particle. And that's 1.38 times 10 to the minus 38, 10 to the minus 23 joules per Kelvin. And then, as the unit suggests, the only thing we got to do is turn this into Kelvin. So 293.15 Kelvin. And voila, this is why you see things in the universal gas constants as joules, is because of the ultimate identification of this with energy, kinetic energy. Okay. And so that will give me about 6.06 times 10 to the minus 21st joules. So the places that you might trip up on this are the units and the per particle. So this is literally the energy for a single average particle. What's weird is, maybe no particle itself actually has that energy. This is kind of the center of a probability distribution. In the same way that you could have a whole bunch of people in a classroom and their average age could be 21.3, but nobody's actually 21.3. So this is average per particle. Okay, this is a little bit of a stretch, but let's use this to estimate. And the reason it's an estimate is because oxygen is not a monatomic ideal gas particle. But it'll give us an order of magnitude right answer. So oxygen. This is a good thing to know and have kind of in the back of your mind. What is the approximate speed of the average air molecule? If we ever get like thunder, you have an experiment that tells you the answer. So it should be the same, roughly speaking, as the speed of sound in that medium. So because sound is transferred by the motion of the gas molecules. So we should get something on the like hundreds of meters per second order if we do this right. So okay, we have is 3 halves kT is 1/2 mv squared, but we already figured out 3 halves kT. Because this is only for monatomic ideal gases, I'm going to do a sensible thing and a semantic thing. I'm going to write the squiggly equals because this is probably order of magnitude good, and I'm not going to bother with more than 1 sig fig. So basically the story of why oxygen isn't perfectly described by this is that it can also store energy by spinning around, because it's basically 2 oxygens on a stick. Okay, so we found that, and basically we just plug it into 1/2 m. We now know how to get m in grams or something like that. And I'm going to write this in the way that we first described it, and then I'm going to rephrase this as RMS in a second. So what is the mass of oxygen? There are 2 things with 16 atomic mass units. So that's 32 AMU, and I have joules, so I got to use SI. So that's 1.6 times 10 to the minus 27 kilograms per AMU. Basically the mass of a proton. And then V average squared is what we're looking for. And then math happens, and I get everything in SI, the AMU cancel out. That's good. I should get V hat squared, 16 Okay, I'll just leave it at 1. We'll say it's about 400 meters per second. Okay, so you should get something on the order of that, which is about the speed of sound, so that's pretty reasonable. Okay, new terminology, so, whoops. Yeah, let me write this in the way that makes it manifest why we want to use new terminology for this. So, okay, I had an average and a square. So this actually average should be first. I averaged, then I squared, and then I square rooted. So picking through this, what I have is, yeah, that was fine. Root mean squared, or RMS. So instead of drawing the radical sign, the overbar for statistical average in the square, we're just going to call this RMS. And it's really just a fancy way of saying average. It's a particular type of average. Okay. Okay, so what is it that we really calculated in some sense? This is the RMS, and I'll draw this. We'll pick into it a little bit. I'll save this for, I think, a project, is what these distributions actually mean. Is if you looked at the actual, at some particular speed, and the thing about this is speed has an x and a y and a z component, right? And speed is always positive, it's just the magnitude of velocity. You'd actually get something in or any other type of gas that looked like this, and if you heated it up, the whole thing would shift to the right. And I'm not bad at drawing bell curves. This is really supposed to actually be skewed, so I'll really exaggerate that actually. So something like that. This is what's called the Maxwell-Boltzmann distribution, and where it balances on your finger is VRMS, which is the thing that we calculated by equating it to the kinetic energy. So imagine this is like a piece of metal and you could balance it on your finger there. So that's what this means. So this is the average. And this is a non-trivial statement, like what this looks like, because if you know the average value of something, you don't know anything else really. So there's a lot more information in the full distribution than the average. So here's the distribution that has the same VRMS. Here's another distribution that has the same VRMS. Right? They would all balance on my finger at that point, but then their details are totally different, right? So this lopsided, weird, up like a quadratic, down like an exponential thing that turns out to really describe these. So we'll talk a bit about that and how to interpret VRMS in the next video before. That's it for chapter 13.